Hello, everyone, and welcome to our webinar series titled Introduction to Photonics Packaging. My name is Mark Rensing, and again, I'm joined by my colleague, Dr. Camilla Gratkowski. And just a brief recap over the last two webinars. So in our first webinar, we provided a general introduction to photonics packaging and package design. And last week, we looked at electrical packaging and thermal management. So in today's webinar, Camille is going to discuss optical packaging and specifically two of the main optical coupling schemes. Again, this webinar will last about 45 minutes and we've allocated 50 minutes at the end for Q&A. So following the same pattern as the last two webinars, please feel free to use the Q&A tab for any questions that you might have, and we'll address them at the end of the talk. So without further ado, I'll hand over to Camille to begin today's webinar.
Everybody, I want to do a mic check to make sure that you can hear us. If you can indicate in the chat or any other methods that we're coming on. Yeah, perfect. Okay. So this is today is essentially the key of the entire photonic packaging. Essentially, all roads lead to optical packaging because this is what differentiates us from the other types of packaging. So in electronics packaging, you essentially deal with electrical signals and the way to deliver them, and also thermal management. However, as I mentioned 2 weeks ago already, optical packaging also has this domain of optics, which we have to take care of. So this is what separates us. Oh, sorry. To laser pointer. Perfect. Okay, so optical packaging is the key to what we do, and essentially the basic principle is very simple. What I'm going to be presenting for most of the time is the edge coupler paradigm, and then briefly at the end I'll also touch on the grating coupler paradigm, but I'll be using edge couplers because they're conceptually a little bit easier to understand. So that's why I'm going to concentrate most of my presentation on this specific one. So in any case, when you're packaging a photonic chip, what you essentially need to do is to deliver optical signal between a fiber and the waveguide. So the waveguides, for example, on silicon can be very small. Their typical size in silicon, as you can see from the image here on the bottom right, there's like 220 by 400 nanometers. So the mode is very tightly squeezed into that waveguide in order to save on space and also have a lower loss propagation. However, optical fibers are typically much bigger, especially when we're working with the, let's say, O and C band domains, so between 1300 and 1550 nanometers. In those cases, the fiber modes are typically much larger. So essentially, photonics packaging is about mediating this optical link and making sure that we can deliver light from the chip and to the chip in as lossless method as possible. So there are various methods of actually doing that. However, before we get to that, we have to just provide a few definitions of what we're working on. So typically when you're working with photonics and photonic integrated circuits, in most cases, I don't know of any cases, but there might be where the signal propagates in a single Gaussian mode. So that's essentially what we'll be narrowing down our scope to, just a single mode Gaussian that's propagating through the waveguide. And as far as definitions that I'll be using, the most critical one is the mode field diameter, which if you take the Gaussian function and you, let's say, put the intensity to unity, and then you take as the central position also put to 0. And if you, instead of x here, put this parameter w, then what you arrive here that the intensity at this parameter w, which is called width, is equal to 1 over e squared, which is about 13.5% of the intensity at peak. So from that, we define our mode field diameter as 2 widths, which is over here. And historically, people were mostly using full width of half maximum, which is similar, but exactly it's at at half maximum. And there's a very simple relationship between the two. However, for our purposes, we're concentrating on mode field diameters and what you're going to find in most of the literature. And as I mentioned previously, essentially what we are trying to do is to match the modes between the waveguides. one waveguide is our PIC waveguide, the other waveguide is our fiber. Now, how it's being done, the technicalities of that, those are better left to to PIC designers and to foundries, because as I mentioned previously, at Photonics Packaging, we mostly deal with interfaces. So we have fiber on one side, and the other side provides a chip with what's called a spot size converter, which converts a very small mode that's propagating in the silicon waveguide to something that's a little bit bigger and approximates what's the mode size of our fiber. However, if they're not matched, and they are typically not matched, then we start incurring losses. So these are essentially the overlap integral is the way that you calculate in general, the coupling efficiency. However, for two Gaussian beams, it can be somewhat simplified. So if in the X and Y direction your dimensions are different, then you use this neat equation, which can be simplified to a much simpler form if your mode sizes on both sides are if the mode sizes are symmetrical. So for example, you have a fiber on one side, which are cylindrically symmetrical, so they're typically symmetrical in the X and Y direction. And if by any happy accident on the opaque side, you also have a symmetrical mode, and you can use this neat formula. And of course, if they don't match, then our theta, which is our eta, sorry, which is our losses are less, our coupling efficiency is less than unity. So what I'll be using throughout this talk, I won't be using natural units. I'll be mostly using decibels, which is a logarithmic unit, and the definitions are given here. So if you're talking about coupling efficiency, that's 10 log of eta, and it's typically less, well, it is less than 0. We can't have coupling efficiency greater than 0 by definition. In practical terms, the coupling efficiency is calculated when you perform experiment as essentially a 10 logs of the power that's transmitted through to the reference power that we know that's injected into fiber. And if that power is equal to 1 milliwatt, then their units become dBm. Useful values to know about is that 0 dB coupling efficiency is equal to 100%. 1 dB, which is going to be used mostly throughout this talk, is about 80%. It's actually around 79.4%. And 3 dB is very close to 50%. And 3 dB is, if you're working with microelectronics, then that's the standard notion. So as far as fibers, I'm just not going to explain all of them. However, typically in our work, we deal with a single mode fibers, because as the photonic chip is single mode, then we also want to couple the mode into that PIC using single mode fibers. So for example, at 1550, the single mode fibers operating at ONC band have a core diameter of 8.2 microns. They're actually very, very easy to distinguish from the multi-mode fibers, which core starts around 50 microns and can get pretty large after that. For other applications, for example, you can use ultra-high numerical aperture fibers, which have a smaller core size and a little bit of different composition, which means that the mode size is a little bit different from the ones that you would have from SM58. And in many applications which require polarization, which are polarization sensitive, you also will encounter polarization maintaining fibers. This is just one of the designs. The simplest and the most common. It's called a panda because of the two ears on the sides of the core, which keep the polarization on the same level. So if you want to match the mode between your, let's say, system, which is your fiber or something that's external to your package, and your photonic chip, then you need to match those modes. So for example, at 1550, the mode for diameter in your single mode fiber is around 10.4 microns. But if you have a PIC, which is not uncommon to have PICs with mode for diameters of 3.5 microns, then if you take the equations, then you find out that you have about 5 dB losses per coupling, which might be a little bit too much for you. So there are many ways to match the modes. Historically, the earliest and the still sometimes used is to use a lensed fiber, which essentially has as the name suggests, a lens at the tip, which focuses the beam down to the small, let's say, between 3 and 4 microns in order to match the mode. However, this is mostly used for applications which just have single channels, and you actually necessarily have to do that. Then what you can do an adiabatic taper splice. It's a relatively new technique where you take a single mode fiber of the standard variety and you take a high numerical aperture fiber which has different mode size, and then you do a adiabatic taper splice in between. And the losses that we get from this method are between 0.1 to 0.2 on the splice itself. Then you can get what's called waveguide array to fiber interposers. These are actually technology developed by Team Photonics, where you can actually use silver ion exchange in order to modify locally the refractive index of glass and essentially create waveguides and write them in the lithographic process. So because you can do that, you can actually take one mode size on one side and taper it down to have a different mode size on the other side. You can do that lithographically. In a similar manner, you can do the same with photonic integrated circuits, which are made for this kind of tapering. You can have a chip which has a output coupler that has a mode at the edge, which is varying with distance. You can see here the vernier, which tells you, at the position at which the mode is approximately which size. So here at this distance, it's 3 microns, 4 microns, and so on, and you polish it down until you arrive at the value that's of interest. This technology was developed by Fix. So unfortunately, if that was the end of it, this wouldn't be so difficult. However, unfortunately, in many applications, you also have to worry about relative position of the modes between the fiber and the chip. As you'll see, those tolerances, as we call them, are quite small. And the theory behind this is quite simple. As one of the mode gets displaced, whether in vertical or horizontal direction, then the modes shift relative to one another, and you start incurring losses, in which case your coupling efficiency becomes less than 1. If you perform very simple Zemax simulations where you assume that your mode field diameter on both sides are identical, so let's say your chip is 10 microns mode field diameter and your fiber is 1 micron mode field diameter as well, and you plot it as a function of that mode field diameter, then you arrive at a very interesting solution that the slope of this line is equal 0.24. So in this case, it means that for symmetrical couplers, for identical symmetrical couplers, you can expect your alignment tolerance to be around 1/4 of the mode field diameter. This is actually a useful thing to keep in mind. Of course, this is a simulation that doesn't take into consideration the wave dependence, but the mode field diameter within your fiber, the PIC, the size of the mode will be wave dependent. So in what you would want in order to satisfy this, the fiber and the chip follow the same slope, but of course that rarely happens. In any case, this value of 0.24, it can be actually demonstrated from first principles, and this is actually a graph from a paper that was just accepted to Applied Optics, and I hope it will be published soon, where you can actually demonstrate that your alignment tolerance at 1 dB is approximately nearly identical to 0.24. This parameter here, square root of minus natural logarithm of eta at some specific threshold, is what defines your alignment tolerances. For example, here you can see on this graph that at 1 dB coupling efficiency, you get your benchmark distance, your displacement distance is 0.24. However, if you select your benchmark at 3 dB, then this value then becomes 0.415. So you'll get 3 dB losses when you are 41% off from the size of your mode. So if your mode size is, for example, 10 microns, then your 1 dB losses will be at 2.4 microns, but your 3 dB losses will be at 4.1 microns. Conversely, as you go to much smaller tolerant thresholds, for example, 0.1 dB, you're now entering into very, very tight tolerance regime where, for example, if your mode size is 10 microns, your tolerance to achieve that goal is 0.7 microns. However, with this graph, essentially you can choose any tolerance cutoff point and the scaling law of this type will still apply. You can actually demonstrate that. Of course, reality is not is such that we very rarely have identical couplers and symmetrical couplers on both sides. So what we mostly deal with is some sort of asymmetry. In fibers, they typically, of course, have, because of their inherent symmetry, they have the mode size is symmetrical. However, PICs are not. So this is quite a very simple simulation that kind of demonstrates the principle in general, where we have where we take our mode size in the fiber to be equal to 10.4, and we assume that mode field diameter in the PIC is as well equal to 10.4. And what we get there is that regardless of the mode size of the PIC in the other direction, the tolerance is constant, is completely independent on the mode size in the vertical direction. The black line is the limiting value, that's the slope of 0.24. But what you have is that in the other direction, the vertical direction, the coupling efficiency doesn't follow either this or this line. However, these lines are, let's say, independent. And again, the paper that I mentioned, there's actually derivation of the formula that shows this as well. To give you a little bit of a perspective of how difficult it is to align the fiber to the waveguide, what you saw here, the values that you see here are of the order of 2.5 microns for 1 dB losses. And if you compare that to, for example, a human red blood cell, you can see that the thickness of the blood cell is around 2 microns. So this is the tolerance. This is our accuracy that we have to achieve in order to align the fiber to the chip and be still within more or less 1 dB coupling efficiency. So that's for the displacement. There are also other axes that we have to typically deal with. One of them is rotation. So if we perform a similar analysis where we, for starters, assume that all mode field diameters are exactly the same across the entire system, and we plot our 1 dB alignment tolerance against the mode field, and they select the mode field diameter, then we get this curve, which doesn't seem to look like anything until you actually plot it in the reciprocal space, in which you get a straight line. And you can actually show that this line is because it's tied to the divergence angle of the Gaussian beam, which is defined using this formula. And again, derivation of this is in the paper. And if you also add another magisterium of the wavelength, you also see similar performance, that as your wavelength increases, so does your alignment tolerance increases. However, what's important to understand to remember from these is that as your mode field diameter increases, your angular alignment tolerance decreases. That's unfortunately that's the thing what happens. So as you increase your mode field diameter, you get better at aligning in the X and Y directions, for example, but you lose your angular tolerance. However, if you look at these numbers, so for example, for 10.4 micron mode field diameter, our alignment tolerance in the angle is around 3, it's just shy of 3 degrees. And 3 degrees is very large for photonic packaging machines, so we rarely have to worry about it at all. And just coming back a little bit, again, you can show that the alignment tolerance of angle is essentially tied to your to the divergence angle, and which also includes the wavelength, which is why that we have this wavelength dependence. Of course, this is kind of an idealistic simulation because we assume that the multiple diameter doesn't change as a function of wavelength, and it does. So this is not say idealized case, but it gives you some sort of a understanding. Of course, if you start putting all your realistic numbers, then these straight lines become a little bit more curved. So that's as far as, let's say, theory goes. However, when you go to the experimental data, most likely to mode mismatch and some other effects, what you see is what you can expect ballpark is that your alignment tolerance will end up to being about a third of your multiple diameter that you have in the system. So if you have everything perfectly, matched, then you'll get 1/4 as predicted by theory, but in practice, it comes closer to 1/3. And that's only if you are dealing with a single fiber, which is not so difficult to align and perform optical packaging, but in modern photonics, we also rarely have such a comfortable situation, and typically what we have are multiple channels. The channels right now typically are between 2 and, let's say, 16, and there are some works in the pipeline which tend to increase this number all the way to more than 162. I think the biggest fiber array that we personally dealt with was 138 fibers, but as photonics progresses, we expect these numbers of optical channels going to be significantly larger than what they are currently. And right now, there are in fiber arrays there are 2 pitch standards. One is 127 microns. That's because the size of the cladding of your standard single mode fiber is 125 microns, which means if you leave 1 micron each side from each fiber, that's why you get the 127. And the other pitch standard is 250 microns. And of course, you can derivatives of those. So you can get 500 micron fiber array, 750 micron fiber array, and such. Other pitch standards are also available on demand, but it's currently a little bit more difficult to get something which is pitched at less than 127, although there are some experimental fiber arrays that you can get that use fibers which have a cladding of diameter of just 80 microns. So, but I don't know if we'll be able to get much more down with that diameter. It's possible, but the reliability might suffer, because there are also manufacturing tolerances of the fibers themselves and also of the fiber of the array as it is constructed. So, for example, core concentricity, or how well the core is aligned to the outside cladding, is better than 0.5 micron. That's the typical quotation you'll find. Then there's the pitch tolerance between different or adjacent channels. So depending on the number of channels, this can be from plus or minus 0.7 microns all the way to 1.5 microns if your fiber is sufficiently large. And if you remember that we have around 2.4 microns for coupling to a chip which has at 1550, this tells you that you'll incur some losses, but there might not be egregious. And of course, final tolerance is the polishing angle tolerance. At the angle at which you polish the fibers, that tolerance of that can be between 0.3 and 0.5 degrees. And the more there's an issue in photonics packaging that's been recognized for several years now, and that's that of shoreline density. The more channels you have, the more, let's say, the length of your chip you need to have. For example, if you are pitched at 250 microns and you have, let's take a small number, 20 optical channels, then your baseline, the length of your chip has to be 5 millimeters at the very least in order to support all that. If you have, let's say, you're going towards 120 microns, then you need 30 millimeters. And in photonics, you pay very dearly for real estate. So you have to be very conscious of, how big of a chip do you want to have in order to support that many of channels. And of course, you can reduce the pitch to 127, essentially cutting this in half. But you can also keep reducing the pitch using some other methods. The interposer that I mentioned previously is, for example, the chip interposer, but also the glass interposer. They can be used not only to reduce or modify the size of your mode, but they can also be used to reduce the pitch. So we did a project some time ago, about 6 or 7 years ago, where we used such an interposer which was going from 127 to 63.5 micron pitch, so that we could squeeze a lot of channels into a very small space. So for 120 optical channels, you're already down to, let's say, about 7 millimeters, which is more manageable. So this is how such an optical interposer works. In this case, this is the waft interposer, where you have your optical channels on one side pitched at standard fiber array scale, and then it's being pitched down to match not only the mode size, but also the pitch to match that on your pick. So you can do many interesting things with your interposers. Last week I spoke about electric interposers that can also be used to reduce the pitch of the electric connections, and this is the optical equivalent of that. The next topic that has to be highlighted is when you're talking about edge coppers, is how do you prepare the facets? Because if you don't prepare the facets properly or well, then you'll start incurring losses due to scattering. So the simplest way is just to use a dicing saw or a laser to cut through the wafer. It's fast, scalable, because you can just program your dicing saw on your wafer and just having run wild. However, as you can see from the image here, there is a lot of roughness to the edge, which leads to high scattering, and also, especially with laser, you can have a lot of debris on surface as well. Then you can also use crystallographic planes to break the wafer, which is quite fast. However, if you have a very large wafer, it's actually quite difficult to do to have a neat cleave on the entire wafer. So I believe it's best suited just for laser chips, and not so much for the photonic integrated circuits. Then, if, for example, you dice your wafer, you can then polish it afterwards, which leaves you with very smooth facets. However, it's a slow process, because essentially you have to take your chip one by one, putting in a polishing machine, and then grind it down using different grits until you get the quality of the facet that you need. So it's quite difficult to execute on a large wafer and large scale. And it's quite difficult to see on this image, but this is the image I took several years ago. And if you compare this line, which is the reference line on the chip, that should be parallel to the surface, you can see that the polishing is actually about, in this case, 1 degree off. It's actually very easy to polish at angles which are not perpendicular to your copper. So there's a little bit of a problem when you try and polish. Then recently, the most common method of getting facets, which is actually with this you can get exceptionally good facets, is to perform a chemical wet etch of the face. So what you'd have is your wafer, you take your wafer and then you just etch it down just where your edge coppers are. Of course, you have to pattern it in such a way that you etch in the correct place. And you actually etch it using 2 steps. You can see here, perhaps from this image, that there is a very nice surface which extends perhaps 20 microns down, and then the rest of the face is a little bit more rugged. That's because the 2 different etching solutions are used to create a very nice and smooth facet, and then the rest of it to just etch it down to a specific depth. And afterwards, what you do, you essentially have these trenches, and you use your dicing saw to just dice right in between to have these facets exposed. However, you can see from this SCM image that what this creates is this L-shaped cavity, which is not very good for packaging, because what you need to do in that case is you cannot have a standard fiber array with a lid which is flushed with your fibers. You actually have to get a special fiber made, which has a lid retracted by 0.5 millimeter to 1 millimeter. And with that, you have enough space to actually approach with the fibers to your pick. So this is what you have. If you look from the side of such a pick, you have your pick substrate. This is the L-shaped ledge that was created using etching process. You can see the two steps here. This is the fast step, this is the slow step. And this has to be etched down by at least more than half of the diameter of the fiber, which is 125 microns. So you have to etch down at least 65 microns, if not more. Another way of dealing with that edge issue is undercutting. What you can do is, if you're quite good at it, and we have here specialists that can do this with exceptional accuracy, is you can take your dicing saw and you can dice up until this moment. You just position your blade so that it stops over here, and you can see these grooves are made using the dicing saw coming from the bottom of the chip, and this essentially exposes your facet, so you can approach with a standard fiber. This is a tricky process. I wouldn't perhaps recommend a large scale, but you can deal with if you need to have standard fiber arrays without retractor lid. This is another way of dealing with that. Another dicing method, which is perhaps in my experience gives the best facets, is stealth dicing, where you focus a laser not on the top surface where it would leave debris and jagged lines, but you actually focus it on the sacrificial layer somewhere within the body of the silicon wafer, and then you just scratch it essentially inside, and then you can separate it and break it off. And this method is actually quite good in creating very smooth, as you can see, very smooth facets, very smooth surfaces. And when you compare using the same chip designed, the difference between a saw dicing and stealth dicing is about, in this case, 2 dB. So with saw dicing, we get 3 dB losses per facet at 1550, and with stealth dicing, you get around 1. And if you additionally fill that gap with index matching liquid, then your losses drop to half a dB. Before I finish with edge facets, I need to talk about the special case, which is indium phosphide chips, which since they have monolithic integrated lasers and detectors, typically what you will find with them is that at the edge, the couplers are angled at this. Typically, it's 7 degrees. This is to stop reflection feeding back into laser, because these lasers are modulated, as you can see here, if you remember how to recognize the RF traces. These are modulated at high frequencies. So in order to stop reflections from interfering with the operational laser, these waveguides are angled at 7 degrees. However, this presents a problem for packaging, at least twofold. One is you either have to polish your fiber array at a specific angle, but not only that, you also have to adjust the pitch of your fiber arrays. You no longer can use your standard 127 to 50 microns because of the laws of refraction. So if you crunch the numbers, you'll find out that if, for example, your waveguide pitch on the chip is 250 microns, then your actual fiber array pitch that matches it optically is smaller, 241 microns. So you have to have a very special fiber array made to match this. And if your waveguide pitch would be smaller, then without interposer, you cannot get a fiber array with a standard fiber that would match this pitch, because this is smaller than the size of your fiber. Alternatively, what you could think about is to reverse the problem, where you start with a standard fiber array pitch and then you just adjust your waveguide pitch. However, if I understand correctly, that's foundry PDKs do not really allow to have custom waveguide pitch. So that's for now, that's a no-go. But you can come back to the interposer idea, for example, and have the interposer do all the dirty work for you, where you have your standard fiber array, which is attached to the outside, and the interposer not only matches the pitch, but also matches the angle. And you still have your normal plane of coupling preserved. So this is one of the better ways of dealing with the indium phosphide angled facets. So I'm just going to briefly touch on the grating coppers because from the packaging perspective, whether coupling to the edge or to the grating, there is a very little difference. Let's say theory-wise, you're just matching the modes, matching the angles, and everything has to be, has to be well positioned. With grating coppers, it's actually a little bit easier because you can design them to match the mode size of your fiber a little bit better than you can with edge coppers. With edge coppers, you're dealing with some foundry restrictions and how far you can expand the mode using any sort of spot size converter. So it's a little bit more difficult. Although technology is getting better on that front, and we're getting mode field diameters which are already approaching, let's say, 10 microns at 1550. So we're getting very close. With grating coppers, it's a little bit easier because the principle is a little bit different. Instead of just directly matching the modes, you're using gratings essentially to scatter your light and to interfere in such a way that the light that is, let's say, goes in from the waveguide is coherently scattered in such a way that it leaves the plane of your chip at a specific angle, and much of the power is contained within this beam. Of course, as you can see from the simulation, there are also losses associated with, transmission into the body of the chip. So they're a little bit inherently more lossy than your edge couplers. So historically, grating couplers were a better solution because they had smaller losses than edge couplers. But as the latter became more researched and better technologies were invented, now it's reversed. Now edge couplers have much better coupling efficiency than grating couplers. So here's some videos taken of numerical simulations where we can see the beam from the fiber entering the grating coupler at a specific angle and being coupled in. I'll run that again. You see, yes. So also what you saw very briefly though is some of the beam was transmitted through, and that's the major source of your losses in the system. The element tolerances of fiber to grating coppers are, because you can match the mode a little bit better, they're also quite more relaxed. This is one of the measurements I performed. So what you see here is your element tolerance is around 3 microns, which is congruent with 10 micron mode size. However, the shape is a little bit asymmetric because in this case we had a focusing grating coupler, so the shape of this tolerance curve is also asymmetric. We also have this little bump here in the Z direction, which is this one. It occurs over here when your fiber is positioned over here. And this is actually a reflection from light traveling. So what this point shows is when you retract your fiber towards this side, and what happens there is the light gets transmitted through. This is the silicon oxide silicon boundary, which can reflect part of the light, and it's getting essentially coupled from the bottom. So this is a little bit of a spurious result, but when you're doing optical packaging, you have to be kind of careful in order not to couple, from the wrong side. The coupling efficiency, as I mentioned, is one thing. Right now, the best grating coppers will have around just north of 1 dB losses, I guess. But in comparison to the edge coppers, they have much limited bandwidth. So the edge coppers can be made, they have bandwidth of more than 200 nanometers. Now it's pretty easy to do. However, grating coppers have, due to the coherent nature of their operation, they have much narrower bandwidth. So for this specific example, for example, we have 1 dB bandwidth of 21 nanometers and 3 dB bandwidth of about 39 nanometers. But for each grating coupler from different foundries, different materials, you will see different mileages. Your bandwidths and also losses will vary greatly. Also, grating couplers are not only sensitive to wavelength, but also sensitive to angle. So as you saw from the simulations, they all showed that the beam was not perpendicular to the grating coupler. It was actually coming at a specific angle of incidence. And in standard PDKs, you'll find either 8 degrees or 10 degrees standard angle of incidence. So that's the angle at which you must hit the grating copper to get the best losses. And this graph just shows a simple measurement where it was just the angle of the fiber was modified, and the coupling efficiency is, of course, for this specific coupler is best at 10 degrees because that's the design AOI. But your 1 dB coupling efficiency, your 1 dB angle of incidence tolerance is around 3 degrees, which is kind of congruent with, if you remember the graph I showed before, where at 10 degrees we had about 2.5 degrees tolerance. From theory, that's kind of, it's ballpark there. So if you want to couple your fiber array to the grating coppers, there's 2 ways in which you can do that. One is to go from the top. So you polish your fiber array at the angle which is exactly equal to the AOI, and then just attach it from the top. This is quite simple thing to do, quite simple thing to align and package. However, as you might imagine, this requires quite a tall package because the fiber just sticks out vertically. So if you want to create a low profile package, then this is going to be essentially something that's sticking up at vertically, and there's cable management issues that might arise. Alternatively, you can use total internal reflection, at which you polish your fiber array at a very specific angle, which is given by this formula. And then what you will have is the light travels through the core as is reflected internally from the facet and then is injected into your grating coupler. However, you have to take into consideration that there is a minimum angle of insertion that you can satisfy due to the loss of total internal reflection at the glass to air interface. This also means that when you're packaging such a device, you have to put adhesive underneath over here. But if you have any of that material encroaching on your facet, then you will completely lose your total internal reflection effect. So when you're packaging, be careful not to put any adhesive on the front facet, or your package is not going to work at all. Also, keep in mind that this fiber array is essentially a lidless package, a lidless fiber, because this is the V-groove block. Schematically, this is a V-groove block, and the fiber is just laid into the V-groove block. If there was also a lid on top of it, then the distance between your fiber and your chip would be 1 millimeter, which means that at that distance your beam would spread out quite far, and you need to have a very large grating coppers in order to capture that beam. So for coupling into grating coppers in the horizontal or planar scheme, you need to have lidless fibers. And this is just an example of such a package where you see we have a photonic integrated circuit with an electronic IC integrated on top. And since we wanted this to be quite low profile package, we have this fiber array with a facet polished at, in this case, it was, I believe, 40 degrees to match the angle of incidence. So these packages are quite simple and quite convenient to design. So to summarize the webinar, optical packaging, it differs from the electronic packaging that require great precision, at least as far as positioning in the X and Y direction is. Typically, it will be of the order of single microns, if not less. There are benefits to using both grating coppers and edge coppers, and I touched on some of those already. Right now, the way that things are moving, the edge coppers are going to be better for the future. However, grating coppers have one advantage in that they are surface features. So you can position them. So by positioning them on the surface, you can actually see them better during the alignment process. And also you can utilize surface to have more of your coppers per unit area. While with edge coppers, you just have your edge, which scales your number of copper scales only linearly instead of as a square. And going to another conclusion from this is the best way to minimize the losses is to match the mode field diameter of the copper and the fiber. That's mostly on the on the foundry side, but you can mitigate any mismatches using several techniques, which I touched on briefly, from UHNA fibers, interposer, and such. And we also saw some quite interesting coupler designs, mostly grating couplers, which perform exceptionally well in lab conditions. However, sometimes we're not sure if they're actually a very good solution for packaging. You can get very good coupling for some of the designs, but they might not be very easy to package, or you might not be able to package them at all, at least using the current technology. So that is it for this part of the webinar. Thank you for your attention.